Okay, after overcoming some technical difficulties, I think we can start with the seminar today. We have Yifei Luo from University of California, Santa Cruz. He's doing his PhD in with the Merian Survey, the topic of the talk today. And we discuss a bit your paper in the last journal club at the Institute. So more or less people is kind of familiar. And that's all. And thank you very much. And you can start whenever you want.
Cool. Thank you. Yeah. Thank you for having me. So a great pleasure to have this opportunity to introduce and share our work about the Merian Survey. So the Merian Survey is a pretty new, still ongoing survey. So the primary science goal is about the dwarf galaxies and to construct a large sample of dwarf galaxies to study their dark matter and stellar feedback. Let me first start with giving the credit to our collaborators. So Merian Survey is mainly carried out by people at UC Santa Cruz at Princeton and a bunch of people from other institutions. Today my talk will follow this kind of outline. So I will first give an overview of the Merian Survey and start with the science goal and also kind of a survey design overview and some science from the Merian Survey. Just give you a very brief idea what the Merian Survey does. So Merian Survey is, as I introduced again, so it's the core science goal is to get a lot of star-forming dwarf galaxies between 10 to the 8, 10 to the 9 solar masses at redshift 0.1. So we got about 16 nights on the dark energy camera. So that's a 4-meter telescope, a large field of view imaging camera on the Blanco telescope in Chile. We made 2 custom-made filters. Actually, they are medium band filters. Those green and red filters shown here. I think people here are familiar with the medium band filters. So they are targeting at the Halpha and OIII emission lines at this redshift range. Our survey will cover about 800 square degree on the sky within the HSC, the hyperspectral SSP wide field. That's basically the telescope we use. We use the Blanco telescope to do the imaging survey and a bunch of larger, say, CAC and Magellan telescope to do the follow-up the calibration for the spectra. This is an overview with the depth. So since we are follow-up, basically the HSC field, we automatically got all the photometry from HSC. So that's basically 26, 25 magnitude in the optical. And HSC got a fantastic SING. So by median SING of about 0.6 arcsecond. For Merian, because we are using the Blanco, and the medium band is a little bit shallower. It's like 24 to 23rd magnitude and a slightly larger SING. So this is just an overview of the survey. So now I'm gonna go back a little bit to talk about the science and the motivation why we want to do this survey. So we all know from the standard of the lambda CDM cosmology, it's been really successful on the large scale. So from different aspect of the science, all the way from the CMB, the large scale structure, the galaxy clusters, and from those large scales, the lambda CDM has been really successful. However, since like the recent 2 decades, we have been finding some challenges to the lambda CDM. One challenge is on the small scale. So there are a bunch of papers starting from like late 20 century. Say like 2003, 2004, and also the past decades. There are a bunch of paper talk about the challenges on the lambda CDM on small scales, especially the dwarf galaxies, from different aspects. So people might be familiar with some kind of so-called cost core discrepancy on dwarf galaxies, and also kind of the discrepancy on stellar halo mass relation on the small scale. There's been some discrepancy between the simulation and the observations. This has been a really good review by James Bullock and its collaborator 2017 talk about a bunch of challenges on the dwarf galaxy on the lambda CDM. So just give you a rough idea. So this is the so-called cusp core discrepancy, the discrepancy as a function of the stellar mass to halo mass ratio. So the largest discrepancy is basically around 10 to the 8, 10 to the 9 solar masses. So that's the Merian mass range, what we are probing. So that's basically the largest discrepancy for this kind, the cusp core discrepancy. That's basically one of the reasons why we are interested in those dwarf galaxies, because basically their halo property observed versus simulated are kind of different. Another kind of interesting thing why we are kind of interested in the dwarf galaxy regime is also from the galaxy formation side, because from the hierarchical clustering, we know basically all the galaxies are or have been a dwarf galaxy at one stage of their lifetime. So basically study the dwarf galaxies can help us better understand, the galaxy property, how, the size, their size evolution, like the structural formation, star formation, and also the interaction between like the galaxy and the halo properties. Okay, now, so how we measure the dwarf galaxies, or just the dark matter halo properties for any galaxies. So this has been like a few decades since people first used the rotation curve to measure the dwarf, the dark matter halo of a galaxy. So so the rotation curve is kind of a classical way to study the dark matter halo profile. It's powerful. It can measure a single dark matter halo. It can go all the way to the very center of the halo by just measuring the stars and the gas or this global cluster, any baryon, to the center of the dark matter halo. So that's the advantages. It's also been some disadvantages. So first of all, we know basically the baryon, the stars, the gas, only occupy a very central region of the dark matter halo. So few, kiloparsec or just a few tenths of the kiloparsec. So that's not the full region of the halo. So basically, if you want to say measure a global halo property for example, a total halo mass, you need to extrapolate your central, say, rotation curve to the outer region by some, models to get global halo properties. And also, there's some disadvantage about the kinematics, because to measure the dark matter halo property from rotation curve, you first need to understand the rotation. However, not all galaxies have a, say, ordered rotation, especially for dwarf galaxies. They can be, say, disordered, can be, disturbed by kind of like interaction or stellar feedback. So the rotation curve can be very complicated to measure, to calibrate, and to measure the halo properties. So alternatively, there's another technique called gravitational lensing. I'm pretty sure people here also, some of you are also familiar with this concept. So weak gravitational lensing is basically from the general relativity. We know the light from background galaxies, when they transmit from like a kind of a mass here, a galaxy or galaxy cluster, or basically any shear or any kind of mass, or can be bent or kind of distorted by the mass. So basically, we can use this technique, the gravitational lensing. And here, when I talk about lensing, it's particular the weak gravitational lensing. So it's basically we measure the lensing, the distortion of the background galaxies to derive the mass, or the total mass of the lens galaxies. And so in this way, we can measure basically the whole dark matter halo, say, properties of those lens galaxies. In our case, that will be the dwarf galaxies or dwarf halos, to basically the halo radius. So not only the very central part that only can be measured from the rotation curves. But the thing is, for the weak lensing technique, we need kind of a large sample to stack, because for the weak lensing part, the galaxy part, lensing part, the signal from one halo is pretty low. So we need a large kind of sample to stack to get a good signal. So that's kind of a disadvantage for the lensing part, but it's a really powerful technique, and there's really lots of ongoing weak lensing project to study all kind of like the dark matter and dark energy, something like that. So back to our dwarf galaxy. This is kind of a sample of dwarf galaxy in the nearby universe. So that's a sample of dwarf galaxy below redshift 0.2, between solar mass 10 to the 8 and 10 to the 9 solar masses. So give you a basic idea how those dwarf galaxies, their basic properties look like. For example, their apparent magnitude in I band can go all the way to 24th magnitude. So it's pretty faint, for any spectroscopy survey, and even for some imaging survey, they're pretty faint, 24th magnitude. And they also, in this mass range, many of them are star forming. So you see they're pretty blue in the UMSR color, or you can also see they're like a specific star formation rate. Most of them are star forming. And their half-life radius is kind of small, but not really small, because you see there can be like few arc second. So some of them can be a point source in a ground-based telescope. Some of them can be resolved. So this is a basic idea of the dwarf galaxy, say nearby dwarf galaxy properties. So now, if we want to build a really large sample for those kind of dwarf galaxies, what can we do, or what kind of telescope or survey we want? So that's a question about if there's a existing deep survey to do lensing for those dwarf galaxies. So this is completeness figure in a previous paper we wrote in 2020. So you see, this is a stellar mass as a function of redshift, and the solid line here is the completeness from the HSC, the hyperspectrum, and also there's a surface brightness effect. So basically, everything above those are complete for HSC, and you can also see some dashed lines. So that's for say LSST, the Rubin Observatory, the Euclid, Cosmos, and W first. So the solid lines are from Cosmos, HSC, and Euclid, and dashed line for the LSST and W first, the Roman telescope. So as you can see, basically there's a sweet spot below redshift, say 0.2 for those dwarf galaxies. When I say dwarf galaxies, I mean low mass galaxies below 10 to the 9 solar masses. And of course, there's more even low mass dwarf galaxies, but as you can see, they're not complete, even for those existing or incoming future deep lensing surveys. So there's a sweet spot around, say, redshift 0.1, or in general below redshift 0.2, and in stellar mass below 10 to the 9 solar masses. You can kind of find a large and mass complete sample in this redshift range to study their, to get a large sample to, say, measure the weak lensing signal and study the dwarf halo properties. So we want to kind of estimate how good we can get. So basically, how well we can measure their dwarf halo properties with this kind of sample, if we can get all the dwarf galaxies within this mass range for, say, some future surveys. So we started from measuring or estimating their weak lensing signal to noise. So basically, this is a formula or equation we use to estimate the uncertainty of the weak lensing signal. Basically, the weak lensing signal to noise is dominated or affected by the number of the lens galaxies. So the more lens galaxies you have, the better signal to noise you have. So basically, that's why we stack the lenses to get stack the weak lensing signal around lots of lensed galaxies or a lot of dwarf galaxies to get a good lensing signal to noise. So with this kind of equation, we can, given the number of dwarf galaxies or the number of lenses, we can have a rough estimation of the weak lensing signal to noise. So we measure we estimate the weak lensing signal to noise for 4 different surveys. So HSC wide, Euclid, W-FIRST, and LSST. For 2 kind of dwarf halos. So one is like about 10 to the 8 solar masses and about 10 to the 9 solar masses. So we know those 4 different surveys have different depths and different say survey area. So basically, different depth and different survey area give you different cosmological volume. And basically, if we can we can detect all the dwarf galaxies or dwarf halos in those volume, we can have a rough estimate of their weak lensing signal to noise. So here I give you a summary of their predicted weak lensing signal to noise. So as you can see, for 10 to the 8 stellar mass dwarf galaxy, you can already get a weak lensing signal to noise about 40 for HSC wide, and HSC is basically finished. So we already have the data there. And for like 10 to the 8, it's about 40, 10 to the 9, also like 46, 45. And for future surveys like LS or Rubin Observatory or Roman telescope, you can get even better, much higher signal to noise measurement. So really, we are entering the regime of, measuring the weak lensing signal around dwarf galaxy, which has not been done from previous lensing surveys because of the depths. So basically, as I said here, for the first time we have surveys are both deep and wide enough. So deep because we need to detect those dwarf galaxies, and wide we need a large sample, a large cosmological volume to have enough dwarf galaxy to stack to get their weak lensing signal. And those galaxies are at about the redshift 0.1 because we need to be complete. But the thing is, there's a problem because in the forecast here, we assume we can detect all the dwarf galaxies in those surveys, and we assume we can get their precise distance measurement, so basically a precise redshift. But the thing is, for all of those surveys and all the incoming, say, deep lensing survey, deep and wide lensing survey, they are broadband surveys. Say, for example, like HSC or Euclid or Roman or Rubin, they're all broadband imaging surveys. So basically, we can only get the redshifts from broadband photometric redshifts. So that's not good at redshift 0.1, not good at all. So now the question is, how can we get the measurement of the distance? Because we need the redshift, we need the distance to measure the weak lensing signal. So here the question, so this is basically what's the motivation for the Merian survey. We try to measure the redshift, the photo Z, and detect those dwarf galaxies to do the lensing. All right, so here comes a concept of photo Z. So I'm pretty sure people here are familiar with, because of the JPAS survey and all the other science. But I am still gonna briefly introduce this concept. So basically, for the broadband photo Z, we measure kind of the feature of the spectra on different galaxies. For example, one strong feature is the 4,000 angstrom break. For massive galaxies or quiescent galaxies, you see this very strong feature. And when the feature move in and out to like a filter, for example, here like G-band or R-band broadband filter, you will see difference in their SEDs. So basically, you can do some kind of SED fitting or photo Z code to derive their redshifts. But this technique, is well used from lots of, say, lensing survey, for example, HSC or DES. But the thing is, it's not really good for our primary science, i.e. those dwarf galaxies at redshift 0.1. So the first thing is redshift 0.1 is too low for the 4,000 angstrom break to shift, especially for HSC, because HSC only starts from G-band. It doesn't have a U-band. And there isn't a really deep and also wide U-band survey on the sky comparing to HSC. Remember, HSC go all the way to 26 magnitude, and the bluest is G-band. So there's isn't a U-band. So we cannot see the 4,000 angstrom break between U-band and G-band for those dwarf galaxies. And also dwarf galaxy in general, even we have a U-band dwarf galaxy in general, a pretty low D4000 or 4,000 angstrom break because of their young age and the low metallicity, and basically their stellar population is pretty flat. So this broadband photometry redshift technique is not optimal for those dwarf galaxies. Another alternative way is to use some kind of machine learning technique with existing broadband photometry. So this is kind of a pathway we tried to see if we can just use some existing broadband photometry from HSC to find those dwarf galaxies at redshift 0.1. It turns out it's not good at all. So basically, as you can see, if we build some kind of a simple random forest, say machine learning algorithm, we can only get a 50% completeness of dwarf galaxies with 50% purity. So that's not good at all. And that will leave you about 1,000 dwarf galaxies candidates per square degree on the sky. And the real number density is about like 220 per square degree. So it's not good. However, it can be used to say do some follow-up spectroscopy survey. For example, there's some existing survey called, for example, the Saga survey is doing something similar. So they use some kind of a machine learning technique and do the follow-up with spectra. SPEC-Z survey. However, this kind of, oh, by the way, so this is a random forest where I also try some more, say, fancier algorithm like a CNN or DNN, deep learning or imaging-based deep learning techniques, but it's not improving a lot. So basically, machine learning, we think it's not good enough. So how about the SPEC-Z survey or SPEC-Z follow-up? So the thing is, for our dwarf galaxies are really faint, so we can only use some kind of 8 or 10 meter class telescope, for example, CAC, which here at University of California we have access to. We did some kind of estimation. Also, we applied for a bunch of CAC nights for test. Turns out we need like 100 full nights on CAC for 100,000 dwarf galaxies. So that's too expensive. I can never graduate with this kind of survey. So we kind of grade, and this is another estimation on a smaller telescope, Magellan, 6.5 meter telescope. You need even longer exposure. However, it's a larger field of view, so you get more galaxies at the same time, but still you need a very long, say, survey to complete a fairly large sample of dwarf galaxies. So also kind of think this SPEC-Z survey is too expensive. However, for future SPEC-Z survey, for example, PSF or DESI-2, actually, the second stage of DESI, it might be possible, but still we don't have those survey yet. But for existing large telescopes, they're not good enough. So here comes to the idea of the medium band or narrow band survey for those dwarf galaxies. The very reason or one important reason is for those dwarf galaxies in this mass range, 10 to the 9 solar masses, they're mostly star forming. According to some previous work, for example, the Saga survey from Mao et al. 2021, also Malakiha 2012 paper, and also some simulation. Those dwarf galaxies 10 to the 8, 10 to the 9 solar masses from observations are, most of them are star forming. The quenching fraction are pretty low. They're like below 10% for field or for isolated dwarf galaxies, and even for the satellite galaxies in this mass range, because they are massive enough, their gravitational potential well are deep enough, so they are basically star forming. They have enough cold gas to form stars. So that means we will have strong emission lines for those dwarf galaxies. And of course, people here know, like with emission lines, we can use some narrowband or medium band filters to help to improve the photometric redshift of those dwarf galaxies. And since we're really, interested in those dwarfs, and we decide to use those deep and wide existing surveys, such as HSC, they already have the broadband, photometry for us. So we can just add up, say, several more medium band or narrow band filters to help to specifically target at those emission lines and use the broadband filters from those surveys like HSC to help characterize the full SED of the dwarfs. Okay, so that's it's the basic idea. And now I'm going to introduce how we design those medium band or narrow band filters. So we started with build a library of dwarf SEDs with the Cosmos 30-band photometry. So Cosmos is it's a 30-band photometry survey. Well, actually, it's not one survey. It's a combination of lots of broadband, medium band, narrow band survey in the Cosmos region, pretty deep, all the way down to 26, 27 magnitude in optical, and all the way from ultraviolet to infrared. So it's a really nice DECam the say a multi-wavelength survey. So we use this Cosmos 30 band survey to build a complete SED library for those dwarf galaxies with some kind of SED fitting code. Here I'm using Prospector. So I also generate some say emission lines from the SED fitting. So you see the red histogram is the H alpha equivalent width distribution from the mock SED, comparing to so 11 Hogs is a nearby dwarf galaxy survey with H alpha. It's pretty similar with the observed say H alpha distribution, and then we simulate the dwarf galaxy images with emission lines with some imaging survey, imaging simulator called Gaussian. So now we basically have a dwarf galaxy image with noise, with sky background, everything looks like a real dwarf galaxy, and their SED. So basically, we can measure a mock photometry for those dwarf galaxies given any filter transmission curve. So the basic idea to design the Merian filter set is a trade-off between the filter central wavelengths and filter width. So for lensing, basically we can detect those dwarf galaxies or emission lines. Think about emission line located within those filter transmission curve in the wavelength space. If the filtered say central wavelength is say higher or longer, you will have higher redshift range or higher redshift higher central redshift for those emission line or those dwarf galaxies. And if the filter width is larger, that means the say wavelength range or the corresponding redshift range for the emission line is also larger. So that means their cosmological volume is also large. However, given say exposure time or given number of nights, that means you will have smaller say survey area given the exposure time, because those dwarf galaxies are faint. So we need say kind of longer exposure if the filter is wider or at higher redshifts because they are fainter. So basically, we want to find the optimal design of the Merian filter set to optimize the observed signal to noise of the dwarf and also their weak lensing signal noise. And remind you, the weak lensing signal noise depend on the number of the dwarf galaxies. So the weak lensing signal to noise prefer more dwarfs and say larger cosmological volume. However, we need to detect them. So so this is basically a trade-off or an optimization for the filter design. So we run a multicolor simulation for the filter set, different filter sets. So this plot is the filter width versus the filter center for each alpha. So filter width is in angstrom, and the filter center for the H alpha on the top is in central angstrom, and on the top is in the central redshift for H alpha. So you see, and this is colored by the lensing signal to noise. So basically, for each given filter set, we know what's the cosmological volume given basically the wavelength range of the filter, and use some kind of mass function of the dwarf. We know roughly how many dwarf lenses are there within that cosmological volume, and then we can estimate the weak lensing signal to noise based on the formula I showed a few minutes ago. And basically, I can color the weak lensing signal to noise. So you can see there's a maximum here. And the black star here is the final Merian filter design. So it's basically for H alpha about redshift 0.08, basically, and the filter width about 300 angstrom. So this is basically the sweet spot for the Merian survey to detect those dwarf galaxies and measure their wavelength signal. Okay, and here I also show you the number of dwarf lenses. As I mentioned before, the wavelength signal noise depend on the number of lenses. So you see also this kind of design have the most dwarf lenses to stack. Okay. So now I give you the overview again. Our H alpha and O3 filter for Merian survey. So that's N708 for H alpha and N540 for O3. So the filter are made by Asahi Filter Company in Japan. So this is actually the actual filter transmission curve measured from the telescope for N540 and N708. And also you see the background, the HSC broadband filters. Okay, so there's a coincidence, well, not really a coincidence, but you can see our N540 and N708 just between the broadband, the G band and R band and I band of HSC. So that's can also improve and help the photo Z for HSC. For even like other galaxies. Okay, so this is the corresponding dwarf galaxy for Merian, so also 10 to the 8, 10 to 9 solar masses, but narrower redshift range, because that's the corresponding redshift range for the Merian filter set. We didn't go all the way to 24th magnitude. Instead, we go to say 23rd or 22nd 0.5 magnitude, or actually 23rd for the faint end. And also they are basically star forming. So that's our Merian target dwarf galaxies, star forming dwarf galaxies 10 to the 8, 10 to 9 solar masses and below redshift 0.1. Okay. So now I give you some mock photometry or mock color for the N708 between HSC broadband filters. So that's I band from HSC minus Merian N708 from our mock image simulators for dwarf galaxies in, or not dwarf, but all the galaxies in the cosmos field. So you see there's within our redshift range, there are those axes between I band and N708. So that's basically the feature we want. Basically you see there's some interlopers at higher redshifts. So this redshift, say 0.1 is our target redshift range. However, there are interlopers at say redshift 0.4. So that's O3 H beta emission line shifted into our N708 filter. So we need another filter, the N540 filter, to help characterizing those interlopers and help the improve the photo Z. So I guess that's also the point for the JPath survey. However, you guys have much more narrowband filter, which is I would say much better for this case. So this is another look for the I minus N708 and R minus N540 as a function of redshift for the mock data. So you see lots of say axes at redshift 0.1 and also 0.4, and some axes at redshift say 0.9. So those are the O2 emitters, and all the way to redshift say 1.5 and even higher redshift, which I will show in a minute. And you can also see those features. Those are the 4,000 angstrom break. So basically, with those say unique features at each the different redshift range, we can measure the photometric redshift of photoses for those galaxies with our Merian medium and filters in 708 and 540. Okay, so this is mock photoses. So on the left, I'm showing you the 5 broadband photoses from HSC on the y-axis as a function versus the true Cosmos 30-band photoses. So it's basically the species. So you can see the 5 broadband photoses are really bad. They are almost uniformly spread in this space. And the black box is our Merian redshift range, so our Merian target dwarf galaxies redshift range. It's really bad. However, on the right is the Merian 7-band photosy versus the true redshift. It's much better than the 5-band photosy, and well, as you can see, it's not great. It's not really one-to-one, but it's already good enough for wavelengthing measurement. So the photosy uncertainty, photosy precision is about 0.01. So it's almost close to a low spectral resolution Gaussian. So we're pretty happy with this photosy precision with Merian 7-band photoses. Okay, so all right, so this is the filter, the actual filter we made. So and install on the dark energy camera. So for a 4-meter telescope, basically the focal length for this telescope is about 1 meter. So it's a large piece of glass. So we also measure the filter transmission curve. So we know the filter transmission curve at different position of the mirror can have, or of the glass can have slightly shift of their central wavelengths. And this can, to some extent, affect our photosy precision, but it's within our, say, photosy, say, uncertainty. So it's basically, I would say, good enough for that large piece of glass. Okay, so the overview for the survey. So we started from 2021. Oh, sorry, I didn't update the number. So we actually already passed the half point of the survey. So I believe we now is like 44 nights already. So we was hoping to finish by the end of this year, but it turns out we might need another semester. So that will be spring 2024. So we want to cover the Merian, the HSC wide field for about 800 square degree, and we also have a deep field, which is basically the Cosmos field, about 2 square degree with much deeper Merian exposure. So this is also kind of an old exposure, but I mean exposure map. But that's basically what we have. And also DECam now is really efficient. You can observe at home. The remote observing is really good for DECam. Some raw data, really good for, so for example, this is a galaxy at within our Merian redshift range. So a basic comparison between different survey, the old SDSS, DECals, HSC, and Merian. And also just remind you, this is only just one exposure. So that's 10 minutes, single exposure. So really pretty good for this kind of star-forming galaxy. And this is the final say view of this star-forming galaxy. So as you can see, the Merian N708 really say find those tiny little dots. So these red dots, those are the star-forming region of this galaxy. By the way, this galaxy is not a dwarf galaxy. This is beautiful spiral galaxies. And you can see those basically star-forming H2 regions with very bright dots in N708 images. Okay, and we reduce the data. So this is a color version, another color version of HSC plus Merian color image. So we reduce data with the Rubin LSST pipeline. With the help of our collaborators in Princeton, so we are able to use the future actually ongoing developing LSST pipeline to install for our Merian data. So it's actually one of the first use of the LSST pipeline to ongoing real data. Well, actually, HSC is also kind of a science case, but HSC is a modified version of LSST pipe. So this is kind of the first set real Merian data in the same way of the Mach photometry I showed before. I-N708 and R-N540 as a function of redshift. So those are real galaxy, real photometry, and real species. So they are actually spectroscopy redshifts from Gamma survey and the cosmos. So you see, basically, we are actually probing those flux axes pretty good, I would say, for those Merian redshift range. And just give you an idea comparing to our Mach. You see some, like outliers here. Those are those can be some blended galaxies or just bad photometry. In the Mach photometry, we don't have uncertainty or errors, but in reality, we will have some uncertainty. But nevertheless, they are a small fraction of the galaxies, of the target galaxies. So we're good. Let's see. You have sometimes I will briefly give you an idea of the Merian first kind of science results. So we're still working on this, but this is the Merian Merian photosy as a function of species. So that's the real Merian photosy, not the Mach one. So now we are able to measure the Merian photosy of a photosy precision of 0.05. And remember, our goal was 0.01, but that's based on some non-error. We didn't consider the uncertainty or error of the photometry. So in reality, there's some like a little bit higher precision, or not higher precision, but worse precision. But that's still a preliminary photosy precision. We're still working on this. I think we still can improve a little bit the photosy precision. And with the existing photosy precision, we can already measure the wave cleansing signal around the dwarf galaxies. So this is a very preliminary figure. I believe this is the first time I show this to people outside of our collaboration. So this is a measured wave cleansing signal for dwarf galaxies between 10 to 8, 10 to 9 solar masses with a very small amount of Merian data. So it's only 50 square degree. And remember, Merian, the goal was to observe about 800 square degrees. So it's really, it's below 10% of our data. So that's really our first set of data. We already have a measurement of the dwarf, wave cleansing signal. So the signal noise is about 4 or 5 sigma. So it's already a pretty solid detection. And I believe we are the first group to measure the, or at least high signal noise wave cleansing signal around those dwarf galaxies. But this is still very preliminary. So yeah, so please just keep an eye on our future papers. I don't know if I still have time on other science goals. So I will just really briefly blink. So we can use the Merian photometry or Merian photosy to do some species follow-ups and to measure their galaxy properties. So actually, we use the Magellan and Keck already collect few thousand spectra, and this is a kind of emission line properties of those dwarf galaxies. So we measure those emission lines spectra with Magellan and Keck, and also we have their Merian images and the HSC broadband images. So basically, we can do the photometry. We can we can see whether we can measure the H alpha or O3 emission lines directly from the image, and we use the spectra to do the calibration. So this is kind of an interesting science. We use the HSC broadband and subtract the Merian narrowband, or actually medium band, and we got a residual. So for example, for those two galaxies, you see the residual pretty clearly. There's a residual, so basically that's H alpha emission for those dwarf galaxies, and we can do a photometry around those blobs, and those should be the H alpha flux directly from the image. So you can imagine this as a really kind of low spectral resolution IFU, but you can have a H alpha map. So that's really good. And we actually calibrate the flux with the spectra we got from Magellan. So they are pretty good agreement in the one-to-one for our Merian redshift range. Okay. Other science, basically for Merian, we can also measure much higher redshifts. So whenever a emission line move into or shift into our Merian redshift or Merian filter, we can see the flux axis. So it turns out our Merian filter can also probe the Lambda alpha emitters at redshift 3.4 and redshift 1.8. So with the Merian, existing photometry, we used Keck and also DESI to measure to observe a few hundred Lambda alpha emitter candidates, and actually we got a pretty good success rate for those Lambda alpha emitters. So here are two examples of those Lambda alpha emitters, and we believe with Merian filters we can also measure those Lambda alpha emitters distribution on the sky. So probably can also probe some proto clusters or just the Lambda alpha nebulae on the sky. So yeah, so this is basically the idea. So for this, and the very last science would be so the Merian survey, the Merian filter can actually help the photosynthesis in general for all the galaxies for HSC, because it's pretty deep, so we can go down to 24. So it's not as deep as HSC, but it's already pretty deep for kind of this kind of lensing survey. So even for non-emission line galaxies, as this plot show, you see for a galaxy that high redshift, say 0.4, 0.8, even all the way to redshift 1, because the Merian redshift Merian filters are between the G, R, and I band, say broadband filters, it can actually help to get say more features for those non-emission line galaxies, say the 4,000 angstrom break or O2 emission, or something like that. So in principle, adding those say narrowband or medium band filters can help future imaging survey like say like LSIT or Rubin observatories or other lensing surveys. And also we can use those medium band photosynthesis to help the target selection for future, say, spectroscopy surveys like DESI2 or PFS. So yeah, so I will leave a summary here and happy to take questions. Thank you.
Thank you very much, Yifei. I still don't have the applause sound effects, but I will incorporate that in the future. So, people having questions, please raise your hand, and I will ask you to talk. I'm sure there will be some questions among the audience. Somebody wants to start, or do I start myself?
Can I ask one? Hello?
Yeah.
Yes.
Go ahead.
So thank you very much. Thank you very much. It was a nice talk. I'm curious about for the part where you showed subtracting the narrowband from the broadband to show the localized star forming region. Do you consider, do you PSF match them first?
Yes.
Yes.
Right. So so that's a very good question. So for the reduction for the LSSD pipe, there's a option that we can first match the PSF between. So that's one reason why we use the LSSD pipeline to reduce the data, because apparently HSC and DECam have very different PSF, and actually DECam, so our median thing is like 0.9 arcsecond. So we first match the PSF and then do the subtraction. Yeah.
Thank you. Thank you.
Right.
Alejandro, go ahead.
Hi. Thank you for the talk. It was really interesting. So I was going. I have a few ideas, a few thoughts. I was going to ask, if I may, about this exactly about this slide, this plot. Just curiosity. What are the points that fall well below the 1-to-1 line especially in the top figure, if you can tell?
So actually those are not in the Merian range. So basically their emission line are not in the filter. That's the point. Because so you see it's actually colored by the redshift. I didn't show the color bar. So they are expected to not follow on the 1-to-1 line, because there isn't an emission line in the medium filter at all. Yeah.
Great. Full disclosure, I have been working on emission line galaxies with the J+ survey, which is a smaller version of JPass, and also has like individual filters. So I feel very close to this kind of plot. I have made it myself, so I wanted to know better. Of course, your observations go way deeper than ours, and I was wondering, because if I think correctly, the stellar masses that that you probe with this, it seems like in the range of 10 to the 8, 10 to the 9. Am I right?
Yeah.
I was expecting you to go to smaller galaxies, if you reach such faint, especially the ones that I'm more interested in, the most star-forming galaxies with the highest, strongest emission lines, etc. So do you go there, but you just are not complete, so you remove them?
So let me show you a figure. So I have some backup slides. For example, here. So or maybe even a previous figure would be fine. Yeah. So basically, the idea is to have a complete sample, and let's see, do I have that here? Yes. So we do indeed already are probing some lower mass galaxies, like 10 to the 7 even, or even some of very extreme star forming galaxies, low mass, like 10 to the even 6.8 or something. But the thing is, they are not complete. They are, I agree, they are really interesting. So there could be some follow-up targets. They plan to do some follow-up spectra observation with like Keck or Magellan for those galaxies. But for lensing, we really need a complete sample. And as you can see, even for 10 to the 8 dwarfs, they can be as thin as say 24 or 23rd magnitude. So for those even lower mass galaxies, 10 to the 7, 10 to the 7.5, they will be very incomplete. So since we're really trying to characterize their say dark matter and the stellar feedback, we do really want a complete sample. Yeah, but I agree. We can definitely do some interesting science, but probably not lensing for those lower mass dwarfs.
Yeah, sorry, I was not focusing on on the lensing. And just a final thing, I was forgetting. Yeah, you mentioned something about DECi follow-up. So you are already providing targets to DECi for their main survey, or this is another program, or yes? Yeah, there's a DECi Accelerate project program. So DECi is actually finishing earlier. So there will be a DECi 2 or actually a DECi 1B. So we know DECi is beyond schedule. So there will be a DECi 1B, say now between 2024 to 2028. So it's not finalized, but we're working on this. So there was a DECi 2 plan meeting several months ago. So they have some call for ancillary program. So basically try to test what will be observed for the next stage of DECi. So we applied and we got actually 6 hours for DECi along with the Saga team, and we got a few thousand spectra for Merian targets. But I don't think DECi is already open for public. I don't think so. But yeah, this is a kind of internal program for DECi. Yeah. Okay, thank you. Thank you very much.
Okay, I have a question. You mentioned that you were using machine learning to try to find the dwarf galaxies in broadband surveys. What were you using to train the machine? Which were you using also the templates or real observations?
We use real observations in Cosmos. So basically, I don't think I have the slides, but so in the Cosmos 30 band catalog, there's a Cosmos 2015 and Cosmos 2020. There are really say basically the 30 band photos give you a really say complete sample and large sample to do the training. But the thing is, I think the reason we didn't get a good say machine learning result is still we are limited to the training sample because of we don't have a really complete dwarf say SED sample large enough to do the training. Yeah.
And have you considered to train the algorithm with real data from narrow bands? Because Alejandro has a catalog, and he will publish further releases with larger samples. So I don't know if that could be an advantage, but that's that's a database that you could use to train the algorithm already with narrow bands to find these targets.
I mean, basically Cosmos 30 band is also narrow band, so it's basically the same concept. It's basically because we use Cosmos because it's there, so that's where we got started. And it definitely will be better if there's more data to train. And given we already have the medium band from Merian already, so I guess it's also helpful for future surveys because. Apparently, there are more future stuff like the Rubin is going on. I would say pretty soon. So yeah, definitely will be helpful for other say future surveys. Yeah.
Okay. Another question is with the sample of dwarfs that you have, do you plan to do some studies regarding the environmental effect on the star formation quenching of dwarfs?
That's a really good question. So it's on our list. the thing is, we need to get a good, say, photo Z precision to say, let's see, do I have the slides? I probably, no. Sorry, but I think, so in my paper, actually, there's a figure so basically we measure the, say, we estimate the correlation function given different, say, photo Z precision. So if we can really have a good photo Z precision as we expect, say, photo Z precision of 0.01, so that's about, if I remember correctly, is 30 or 40 megaparsec in the physical space. And we wanted to use the existing SPECSY sample from existing survey, like Sloan or DESI, and do some cross correlation so we can get the environment, identified for our dwarf, whether they are filled or they are, satellites, and how close they are with their centrals. And then we can study like the, quenching fraction or something like that. But before that, we need our, best photo Z's. But we are still working on that. So I would say the environment or, those kind of science is our next step.
Okay. Carlos has some questions.
Yeah, can you hear me? No.
Yep.
Yeah, great. So first of all, thank you for the talk. I think that is very interesting. We are very close to this kind of science and this kind of data, as you can imagine. Indeed, I saw a lot of the science cases that are planned or are already done with our survey. So I mean, I think that we know about the powerful that this data can be. So I have a couple of questions. Can you go to the figure in which you provide the photometric redshift precision? It's not this one, but they were like a histogram or something like that.
Histogram. Let me see.
I saw it.
Is this one?
Yeah. So at the end, what your redshift range of interest is between 0.06 and 0.1, more or less. So
right.
No, I think that makes sense that there you have this 1% more or less, just because is where you have two lines. When you have the two lines, it's much easier for the code probably to spot the right redshift. Then you have continuum, and even if you include two more filters, I mean, the broadbands are giving you, as you provided in introduction, the Balmer break. So I think that at least at first order, more or less makes sense. I mean, as you say, it's whether you can improve, but I think that at least the good photosees are where they should be, let's say.
Right.
And another question, this is also related with the environment, but in the other way around, in the sense that I guess that to have a meaningful result from the weak lensing, what you want to prove is the one halo term, let's say.
Yes.
Basically, you want isolated dwarfs, because if not, you are probably proving the halo of the bigger galaxy that is around the dwarf. So are you planning to make some isolation criteria?
That's also a really good question. So we are actually trying to make modeling in simulations. So we are running our own in-body simulations and hydro simulations for dwarfs, because basically existing simulations are not, say, good enough for those kind of mass range, but we're running our own for those dwarfs. So we are going to, say, estimate basically make modeling for the 1 halo and 2 halo terms for those dwarfs in simulations, and in general we do the fitting. So, but the thing is, I think there are two things. So one thing I have already mentioned. So if we do some kind of cross correlation with existing SPECSY targets, we can sort of get their environment. And the second thing is we really need to understand the satellite fraction of those dwarfs, because it's also a star formation rate dependent. So if you are really close to a massive galaxy, you can be quenched. But the thing is, we cannot detect those dwarf galaxies because the Merian medium band filter only detects star forming dwarfs. We actually detect them, but the photo for those dwarfs, quiescent dwarfs, would be pretty bad because they don't have emission lines. So yeah, so I think there are just two ways. One way is from the observation, we can get some, environment, say from the photo Z or the cross correlation, and from the simulation side, we can better understand their satellite fraction, or basically the one halo to Heyman term from the simulation, from the modeling. So that's basically the two ways we are going.
Yeah, no, but because it's a very interesting population, but also with a lot of biases in this, as you say, in the selection at the end. But yeah, it's a good.
Yeah, exactly.
And finally, when you present this image in which you subtract, let's say, the continuum of, in which you present the emission image.
Let's see, this one?
Yeah, this one. Yeah, we did something very similar in J+, in the sense that we use the broadbands and assume a linear continuum. So I can pass you some reference in which we make when you make the math, you can more or less have an idea of what should be the combination of the filters to assume a linear continuum, and for example, accounting that H alpha probably is also in the R band or in the I band. So at the end, you can have in principle, better detection image, let's say.
Okay. Cool. Yeah. Actually, this is actually pretty preliminary. So we also have a collaborator at Princeton who's actually doing something more fancier by not using a simple, say, linear combination, but actually do a SED fitting, image-based SED fitting or pixel-based SED fitting. I think that's more fancier, but well, it's not my project, so I don't have the current progress of that. But yeah. This is very interesting.
Yeah, in our case, we use this for, let's say, detection, and then we measure in the original images and make the set fitting. So you can gather higher signal to noise in that sense.
Right. Yeah.
But I can provide you with the reference so you can take a look and
great.
See the
that
ideas
would be great.
there. Okay,
cool.
So thank you very much.
Thank you.
Okay, do we have any more questions? If not, I think we can finish here. Thank you very much.
Maybe one.
Yeah. Okay.
One final last question. So, what's the plan for the public release of the outputs?
Yeah, that's simple answer is I don't know. So the data is already public. So I mean the raw data are already public on the NOAO archive. So that's everyone can have access. The data product, we are writing our say survey paper. So the survey overview paper. So I assume the photometry will also be released, but as I say, so it's only year one. So we now only say reduce the year one data. So there might be a year one data release. Hopefully later by the end of this year, hopefully, but I don't know. It's collaboration, so people might have different ideas. So yeah.
Okay, great. I look forward to it. Thank you.
Okay. So thank you very much, Yifei, for the excellent talk and the impressive amount of work that you have put together.
Okay, thank you.
Bye.
Bye-bye. Thank you.
Bye. Thank you.
Bye. Thank you.